Lesson 9 is exponentials in context, and we're going to start by introducing the formulas that we can use to help us write rules that represent real-life situations that involve exponential functions. So the first one is going to be the general form of an exponential function, which is f of x equals a times b to the x power, where b is, it's the base of the exponential, but it's also the growth factor. So it's like how much is your problem or your situation like increasing or decreasing by. So is it like doubling or tripling or being cut in half or thirds or something like that? That would be B. And then the other two formulas kind of go together. One is going to be for exponential growth and one is for exponential decay, and you can see they look pretty similar. So for exponential growth, it's f of x equals a times 1 plus r to the x power. Sometimes it shows up as like a t in the exponent for time, but the kind of more general version would be x. And then for exponential decay, it's f of x equals a times 1 minus r to the x power. And the only difference between the two is just the situation you would use them for. So if something is like, say, increasing by like 4% each year, or I don't know, increasing by 20% per day, that would be an example of exponential growth. So you would choose the one that has the 1 plus r. And then if you had a problem that was like referring to something decreasing in value or losing its value, then you would use the exponential decay formula. So I would personally use like the exponential growth and decay formulas, the ones that have the 1 plus or minus r, for problems that involve percentages. I think that's kind of the most common place we see them. So you can add a little note for yourself to use these with percentages. And then something to keep in mind is that even if you're given a percent in the problem itself, you need to change it to decimal form before you actually put it in the formula, and we'll kind of see what that looks like in some of the examples. Okay, and then you'll notice that every single one of the formulas has an A in it. So like the general form starts with A, these both start with A. So regardless of the formula, A is going to be the starting amount. Okay, so example 1A, write a rule for each scenario. So A is Sarah tracked the population of rabbits in her neighborhood. At the end of the first year, she counted 20 rabbits. Over the year, the population doubled over the years, the population doubled each year. Okay, so when you have a problem that says like, you know, the population or whatever the like original thing was doubles or triples or whatever that value is, it can be a little bit confusing to use like the exponential growth or decay formula because we think doubling and we want to put in like a 2, but doubling means you're like increasing something by 1%. So I wouldn't like use r equals 2, I'd have to put in a 1 for 100%. But if I just stick with like this general form, then I don't really have to worry about that in this case, because if something is doubling, that means that the growth factor is 2. So if something is doubling, the growth factor would be 2. If something is tripling, the growth factor would be 3. If it's getting cut in 1/2, the growth factor would be 1/2, and so on. So anytime you have those words like double, triple, and so on, you can use that first formula, the general form. Okay, so we're going to start our rule with f of x. And then the first part of our formula is A, which is supposed to be like how much we're starting with. So it says at the end of the first year, she counted 20 rabbits. So that 20 is going to be A. So we'll put 20 in right here. And then times, next is going to be B, which is going to be our growth factor. We said our growth factor was 2, so we'll put that in here. So times 2. And then raised to the x power. And then in certain cases, depending on what is initially given to you, you have to kind of, I guess, take that into consideration when you're setting up your exponent. So for example, right now, and you don't have to like write this, I'm going to end up erasing it, but right now, if I were to say like, okay, at the end of the first year, I would put a 1 in for x because x is like the years that are going by in this case. That would be 20 times 2 to the first power, which is 40. But it says right here at the end of the first year, she counted 20 rabbits. And then if it's doubling each year, then the end of the second year would be 40. The end of the third year would be 80 and so on. But because we were given that end of the first year, we already had that. We have to take that into consideration when we're writing our exponent. So instead of just x, we're going to do x minus 1. And that's there because we were given the first year. Okay, so now I'm going to just kind of check it one more time as if I were to put in 1 for the first year. So if I put in 1 there for the first year, it would be 20 times 2, and then raised to the 1 minus 1, so that'd be 0. Well, 20 times 2 to the 0 power is 1. 20 times 1 is 20, so that matches up with what we were given in the problem. So it's always good to just kind of double check and make sure that your actual function matches up with the values that you have. You don't always have to do x minus 1 as your exponent as opposed to just x, but typically when you're given that first year, you have to do that to make sure that your first year actually does match up with your function. So our final rule will be f of x equals 20 times 2 raised to the x minus 1. Okay, and then B, Miss Nelson drinks a cup of coffee every morning. In doing so, she takes 75 milligrams of caffeine into her system. The amount of caffeine in a typical adult is reduced at a rate of 21% every hour. Okay, so when we're deciding which type of formula to use, on this one we're given a percentage. So I would recommend choosing one of these ones, exponential growth or decay. And then when you're deciding between those two, because there is a specific one that you need to pick out of those two, you need to look for a keyword that indicates whether it is increasing or decreasing. And this says that the amount of caffeine in a typical adult is reduced at a rate of 21% every hour. So that word reduced is an indicator word for decay. So if you see reduced, that means decay. There's some other words that we'll talk about after this example of just ones to kind of look out for in the problems. So I'm just going to take the exponential decay formula and write it down here. I'm going to end up erasing what kind of values I need to put in. So it'll be f of x equals a times 1 minus r to the x power to start. And then we need to find something for a, the starting amount, and for r, the rate. So a we know is that starting amount. So if we look at back through the problem, it says in doing so, the second sentence, in doing so, she takes 75 milligrams of caffeine into her system. So she starts with 75. So 75 is going to have to go in for A. So we'll put 75 in for A. And then we also need to put something in for R, which is going to be the rate that it's decreasing by. So it decreases by, or it's reduced at a rate of 21% every hour. And before we can put that into the function, we have to change it into decimal form. So anytime something has a percentage symbol next to it, it's in percent form, even if it has a decimal. So even if this was 21.4%, we would still need to change the form. So to do that, 21%, if it's say 21 and the decimal is right there, 21%, you move the decimal place twice to the left to change from percentage to a decimal, or you would take the percentage and divide by 100. So 21 divided by 100 would be 0.21. So where R is, we're going to put in a 0.21. So we'll do 0.21. And then we don't need to put anything in for x because it's supposed to be for any x, any hour that goes by. And then now we just want to kind of finish simplifying our function and get our final rule. So it'll be f of x equals 75. And then 1 minus 0.21 would be 0.79 and then to the x power. So it'd be f of x equals 75 times 0.79 raised to the x power. So some of the other keywords that you want to look for when you're looking for growth versus decay, for growth words that you may see would be increases, appreciates, or gains. Appreciates is one of the ones that's kind of easy to forget because it has two meanings, but appreciates means to increase in value. And then for decay words, It could be like decreases, depreciates, loses, reduces. Again, depreciates kind of one of the harder ones because it means it decreases in value. So moving down to example 2, for this one, we're going to write a rule and then end up solving for a value in each situation. So 2A says the original value of a painting is $13,000 and the value increases by 6% each year. So in this one, it gives us the percentage that it's changing by. So we probably want to use either the exponential growth or decay formulas, one of these up here. And then when we're deciding between whether we should use exponential growth or decay, we want to look for one of those indicator words on if the function is increasing or decreasing. This one just uses the word increases. So the value increases by 6% each year. So we're going to use the exponential growth formula. So I'm going to zoom in and just rewrite it down here. So the formula itself is f of x equals a times 1 plus r to the x power. And a is going to be our starting amount, so we'll have to go through the problem and figure out, okay, where is the value starting? It says the original value of the painting is 13,000, so that's going to go in for a. So I'm going to take out the a and replace it with 13,000. I guess I probably need some more space. So starting value a is 13,000, so we're going to put the 13,000 in there. And then r is the rate that it's increasing by each year. And remember that if we're given it in percentage form, we need to change it to a decimal. So r is 6%, yes, but if I want to convert that to a decimal, so r is 6%. If I want to convert 6% to a decimal, I pretend there is, or not pretend, but there is a decimal place there, and I move it twice to the left, and then that would give me 0.06, or you can take 6 and divide it by 100 to get 0.06 as well. So we're going to take out that r and put in a 0.06. Okay, so one more time, just how we got each value. A is the starting amount, that's this right here. The value of the painting started at $13,000. And then R is the rate that it's increasing by each year. It was 6%, but 6% as a decimal is 0.06. You can find that by taking 6 and dividing by 100. Okay, so we have everything in there now. I'm just going to go ahead and simplify it. So kind of just like adding these two together in here. So it'll be f of x equals 13,000 times 1.06 and then to the x power. Okay, and then for the next section, how many years will it take for the painting to be worth $25,000? So this is written in function notation. In this case, like our input, our kind of like independent variable is time, and that's x. So like this x right here, whatever I put in there is going to be like the amount of years that are going by. So if it's 1, it'd be 1 year, 2 would be 2 years, and so on. This f of x means like the value of the function evaluated at that x value. So what that would mean here is like, say we found f of 1, that would be how much the painting is worth after 1 year. Or if we were finding f of 2, that would give us the value that we're finding, like, or the value that the painting is worth after 2 years, and so on. So that f of x, like the entire thing altogether, is going to be the value of the painting. So to figure out how many years will it take for the painting to be worth $25,000, that means that we have to take $25,000 and we have to put it in for f of x, and we have to solve for x, because that's going to be the amount of years that it takes us to get there. So instead of f of x, it'll be 25,000, and it's not like f of 25,000, it's like the whole function is 25,000, and then equals 13,000 times 1.06 to the x power. Okay, so now we have an exponential equation, meaning that we have a like power raised to, or a base raised to a variable exponent. So we've talked about solving exponential equations before. Really the first step, no matter what, is we got to try to get the exponential isolated, which means that the exponential is just this part. It doesn't involve the 13,000 that's not being raised to the x power. So I'd have to cancel out that 13,000. It's being multiplied. So to cancel out, I'm going to divide both sides by 13,000. So divide both sides by 13,000. When you divide numbers that have a bunch of zeros, the zeros pretty much just like cancel each other out, which is kind of nice. So 25,000 divided by 13,000 would be 25 over 13. And I'm pretty sure that's a decimal that just kind of like repeats. So 25, 25 not repeats, but continues on forever. 25 divided by 13 is like 1.9, so on. I'm just going to leave it like that for right now. So we'll leave it as 25 over 13. And then equals over here, the like 13,000 divided by 13,000 cancels out. And then we just have the 1.06 to the x power. Okay, I'm gonna leave a space right here. I would put a space for yours as well. So now we have the exponential isolated, like it's just 1.06 to the x. So we have to cancel out the exponential by using its inverse, which the inverse of an exponential is a log. So we're gonna log both sides of the equation. And to do that, we have to figure out, okay, what should my base be? It has to match the base of the exponential. So the base of the exponential is 1.06. So I'm gonna log base 1.06 both sides of the equation. So log base 1.06. And I know we haven't used logs that have decimals yet, but you can pick any base that you want, almost any base that you want. So we log base 1.06 both sides. And then over here, the log base 1.06 of 1.06 to the x power, these cancel each other out. And it would leave us with just the x, like just the exponent part. So now we have x isolated, so we just have to figure out what to do with this. So obviously we don't have a log base 1.06 button on the calculator, so we have to use the change of base formula, and it's going to work. It's not going to be different just because like it's of that 25/13th. It's going to work the same exact way. It just looks a little bit uglier. So the change of base formula, remember that like what you're taking the log of goes in the numerator, and the original base goes in the denominator. So we're going to change it to common log. You can use natural log too. So it'd be log of 1.06 in the denominator and log of 25 over 13 in the numerator, which like I made, like it's really ugly, but it's not really our problem. Like it's the calculator's problem to figure out. So we just have to know how to type it in. Okay, so this whole thing can just kind of go in the calculator now. So log of 25 over 13 over log of 1.06. So just be careful when you're typing it in. So we'll do log. Sorry, I'm the calculator for us. So we'll do log of 25 over 13. So to type that in, you could do 25 and then divided by 13 and then just close the parentheses. So 25 divided by 13 is the same thing as 25 over 13. Make sure that you close the parentheses and then hit the division sign and then go back to log and then of 1.06. And then hit enter and you're good. So even though it's like, I know it's really ugly on the paper, it's not too bad. So log of 25/13 over log of 1.06 ended up being about 11.2. So x is approximately 11.2. And then looking at the problem as a whole, it was asking how many years will it take for the painting to be worth 25,000. So this is approximately 11.2 years before the value of, or when the value of the painting hits 25,000. Okay, so B, last problem, Francesco places $2,100 into an investment account that earns, I'm going to change this to 7.5% interest compounded annually. Sorry, I didn't realize that these were like both 6%, so I feel like we need a different percent. So we're given a percentage in this problem, so I would recommend either using the exponential growth or the decay formula. To decide between the two, we have to determine whether that amount that he is investing is going to be increasing or decreasing. So it says that he places the $2,100 into an investment account and it earns 7.5% interest. So that means that his money is earning more money. So it's increasing. So we would want to use the exponential growth formula. So that's f of x equals a times 1 plus r to the x power, where x is going to be like the time that's going by each year, and f of x is going to be how much he has total in his account. So we'll find our starting value. That's going to be A. It says that he places $2,100 into his account, so that's going to be A. So we'll put 2,100 in for A right there, and then we also have to find R, which is going to be the rate that the money is growing by. So it says that it earns 7.5% interest, and this is what I was kind of saying where, like, yes, this has a decimal in it, but because it ends in a percent sign, it's in percent form. So to change it from percent to a decimal, I either do 7.5 divided by 100, or I just move the decimal place twice to the left, so that'd be 0.075. And then that's what we have to put in for r, so it's really important to remember to always change it to decimal form before putting it in the function. Okay, so I'm just going to rewrite the function. I'm not going to worry about it like erasing a and r, so it'll be f of x equals a, which is 2,100, and then times 1 plus r, so it's going to be 1 plus 0.075, so that's 1.075. So we can just kind of do that all in one step since you're just adding 1 to 0.075, just adds it to like the ones place. And then now we have our rule. So f of x equals 2,100 times 1.075 to the x. So just keep in mind for this problem, x will be like the time each year that's going by. And f of x, like what it ends up being, would give you like your total in the account. So if you find like f of 2 and simplify, that would be how much money is in the account after 2 years. Okay, so for the next part, when will the account balance be greater than 4,800? So that word greater is an indicator word for an inequality because it doesn't ask like when will the money in the account be like exactly 4,800. It says when will it be greater. And so we wouldn't use an equal sign, we use some sort of inequality symbol. So to figure out how to write it, we have to figure out where that $4,800 goes. So $4,800 is not like the year number, so we're not going to put it in for x. We'd have to put it in as like kind of like our output or like the entire value of the function, so we'd put it in for f of x. So whatever f of x is going to be like the total money in the account. So we'll take that 4,800 and put it in for f of x. Sorry, that's the worst money symbol I've ever seen. Okay, so we'll take that 4,800, put it in for f of x. I'm going to put an equal sign for now, but we're going to end up changing it. And then equals, the rest of it will stay the same. So 2,100 times 1.075, and then to the x power. Okay, so now we have to pick like what type of symbol to use. It just says greater than, it doesn't say greater than or equal to, so we're going to use either this or this. And when we're deciding between the like two, we have to figure out what side needs to be larger. So this is like whatever this simplifies to after we put in like the x is going to be how much is in his account. So if we put 1, it'll simplify to how much money is in the account after 1 year. If we put 2, it'll simplify to how much is in the account after 2 years. So that green section is like actually the value of the account, and we need that value to be greater than 4,800. So we need the open side to go towards the right. So this is saying 2,100 times 1.05 to the x. That'll simplify as how much money he has in the account. We need that to be greater than 4,800. Okay, so we got like pretty much the hard part done, just picking the correct inequality symbol. And then now we can go ahead and solve. So the steps for solving inequalities for exponentials are the same as equations. So we have to get the exponential isolated. So right now the exponential is just 1.075 to the x power. So I would have to figure out a way to cancel out this 2,100. That 2,100 is being multiplied by the exponential. So I'm going to divide both sides by 2,100. So divide both sides. Remember that when you like divide with the zeros, each one in the numerator cancels out one in the denominator. So you can just kind of cross those off. And then 48 over 21 is what we would have left, and both of those are divisible by 3. So we can reduce that by dividing both by 3. So 48 divided by 3 is 16, and then 21 divided by 3 is 7. And then bring down the inequality symbol. Doesn't like switch directions or anything, so divide by a negative, and then 2,100 divided by itself cancels out. And we're left with 1.075 to the x power. So my ultimate goal is to get x by itself, so I have to figure out a way to cancel out the exponential. So to do that, I would use the inverse of an exponential, which is a log. So I'm going to scooch this over, and then I have to figure out what my base needs to be. The base of the exponential is 1.075, so that's what the base of my log will be. So I'll log base 1.075 both sides of the inequality. So log base 1.075 of 16/7 is less than log base 1.075 of 1.075 to the x power. Sorry, that's a lot to say. Okay, so now on the right side of the inequality, the log and the exponential have the same base, so they cancel each other out, and it would leave us with just x. So we'll have x, bring down our inequality symbol, and then now log base 1.075 of 16/7, obviously we don't have like that base in our calculator, so we would rewrite it using the change of base formula, and then we'll be able to plug it right in. So what we're taking the log of goes in the numerator, so it'd be log of 16/7, and then the original base goes in the denominator, so it would be log of 1.075, and then remember, you can use natural log if you want, you can use common log, it doesn't really matter, as long as you use the formula correctly. Okay, so now this is something that we can plug into the calculator. We just have to be careful to be able to do it all in one step. So we'll do log, and then of 16/7, so okay, sorry. It was bugging out on me. Well, it was my own fault. But okay, so one more time, log, and then the 1, 2, 3 to go back, of 16, and then divided by 7 would be 16/7, because fractions are division. And then make sure you close the parentheses, and then divide again to get the denominator, and then go back to log of 1.075. So that says log of 16/7 divided by log of 1.075, and it's about 11.4. Okay, so the last little like tricky thing about this problem, it's like, yes, about 11.4, but because it says like 11.43, normally like a 3 would not round a 4 up, but if I just put like 11.4, he's not going to quite be up to $4,800 yet, so it's one of those types of problems where we just have to round up naturally. So instead of 11.4, I'm going to put 11.5. And then this is saying that x would have to be greater than 11.5. So you could say like after about 11.5 years. That's when his account will be greater than 4,800. I want to go through that rounding thing one more time because that's kind of weird and it's really just like a case-by-case basis. So we got, in the calculator, we got 11.43. And since like 11.4 is a little bit less than like what our actual answer was, since it's a little bit less than, he wouldn't quite be at $4,800. He'd be a little bit beneath it. So we just have to round up either way to like get to where he is definitely greater than 4,800. So we can say after about 11.5 years, or x is greater than 11.5.